The solid, stable ground of the modern world is a relatively recent development. 4.6 billion years ago, Earth was a glowing expanse of magma being pummeled by massive planetesimal impacts. Geologists call this the Hadean Eon. During this time, the heat from decaying radioactive elements and constant celestial bombardment kept the surface molten and inhospitable. This cross-section illustrates planetary differentiation. Under extreme heat, heavy iron-associated elements, shown as red droplets and the sinking diapir, migrated toward the center, while lighter silicates rose. This rapid separation created the partially solid mantle layer seen here, preventing Earth from remaining a homogeneous molten mass. That layered structure, forged in the chaos of the early Hadean, established the physical blueprint for every geographical feature that followed. This creates a physical contradiction. How did a planet entirely covered in boiling magma cool down enough to hold liquid oceans? Evidence of this transition is found in Western Australia, within the mineral record of Jack Hill's zircon crystals. These crystals survived from the early Earth, carrying chemical signatures from the environment where they first formed, specifically the ratio of oxygen isotopes. Because lighter oxygen-16 evaporates more easily from surface water, a body of water will gradually become enriched with the heavier oxygen-18. The Jack Hill zircons contain this exact heavy oxygen signature, which only occurs in cool, wet, sedimentary environments. This proves that the young Earth cooled much faster than originally assumed. By 4.3 billion years ago, the early planet already supported a solid rocky crust and vast liquid oceans. Deep underground, thermal energy left over from the Hadean Eon churns the mantle. Convection currents in that hot rock drive surface plates in constant motion. In 1912, Alfred Wegener observed matching coastlines across the Atlantic and proposed the theory of continental drift, realizing that our landmasses move across the planet's surface. Roughly 335 million years ago, tectonic forces assembled most of the Earth's continental blocks into a single supercontinent called Pangaea. It was surrounded by the Panthalassa mega-ocean, with a shallow wedge called the Tethys Sea cutting into its side. But this arrangement was temporary. Around 200 million years ago, rising magma along mid-oceanic ridges tore Pangaea apart. The landmass fractured into two massive blocks, Laurasia and Gondwana. As the rift widened, Tethys Sea waters flooded the gap, dividing north from south. The modern map results from that fragmentation, with continents continuing to drift toward new coordinates. Following Gondwana's breakup, the Indian plate broke free and began a rapid trajectory toward the equator. About 50 million years ago, it crashed into the Eurasian plate. Because both continental plates had similar rock densities, neither could be subducted. Instead, the pressure forced the crust to buckle and thrust skyward in a process called orogenesis. The Tethys Sea had once separated these two landmasses. As they collided, the thick layers of sand and mud resting on that ancient ocean floor were compressed and squeezed upward. You can find physical proof of this at the summit of Mount Everest. The highest peak on Earth is capped with marine limestone, containing fossils from that ancient ocean. The world's tallest mountains are essentially the crushed, upthrust remains of a vanished seafloor. Geomorphologists call this concept landscape memory. Modern geography bears the physical imprints of ancient geological processes. When the Himalayas rose, they blocked atmospheric circulation. This massive wall of rock permanently altered global climate patterns, driving the heavy rainfall of the Indian summer monsoon. The combination of extreme altitude and monsoon rain feeds antecedent river systems. These rivers continuously erode the uplifting terrain, transporting heavy sediment from the mountain peaks into the fertile basins below. Every feature we see today, from fertile river valleys to high-altitude deserts, is a byproduct of this continuous cycle of uplift and erosion. The Earth remains an active machine, fueled by internal heat and sculpted by the relentless flow of water. Take a closer look at the terrain around you. It is still in the middle of a transformation billions of years in the making.